This video is for STAT219 Statistics for Biology. The topic is correlation and linear regression. This is a very different topic because up to now, except for some very rare exceptions, we've only looked at one variable at a time, except when we looked at scatter plots. But correlation and linear regression is very different because the idea is it helps us determine relationships between two variables. So this idea of determining whether one variable affects another is at the heart of the search for cause, whether changes in variable x cause a change in variable y. And this quote here from Democritus, ancient philosopher, scientist, said, "I prefer discovering a new law of physics," which more literally meant discovering a cause, than becoming the great king of Persia. He was thought to be a little strange in his time, but he's now recognized as the father of atomic theory, the first one to recognize that matter was composed of atoms. And also his name, Democritus, shows he has a link to the beginnings of democracy. So we begin with scatter plots, as these are the first tool we looked at. Remember, in a scatter plot, we have one dot for each element of the sample, and each dot gives us the indication of the value of two different variables. Here, the weight in pounds and mileage in miles per gallon for cars. So the first point over here is at about 1,000 pounds. So this particular car weighed around 1,000 pounds, but only got 25 miles to the gallon. The one way up here weighed a little bit more, maybe 1,400 pounds, but got 50 miles a gallon. But then way out here, we have a very heavy vehicle at 4,500 pounds, only getting 10 miles to the gallon. So there's a general relationship, the scatter plot shows. As weight goes up, gas mileage goes down. And that's based on the law of physics, but it's not constant, because I can have very light cars with poor gas mileage, depending on what kind of motor they have, etc. So a scatter plot gives us a hint at whether there's a relationship between those two variables, but correlation tells us in some precise way what that relationship is. So correlation between two data sets is nothing more than a measure of our ability to predict the value of one variable from another. When the correlation coefficient is 1, we use R as the standard label for the correlation coefficient. When it's 1, it means we have perfect prediction. There's a straight line relationship. You tell me the value of X and I'll tell you the value of Y. But as we introduce noise into this model, or introduce randomness into this model, we see that now we are losing the ability to predict. There's still a general tendency here, but I have a little less ability to predict, and that's reflected in a lower correlation coefficient, 0.66. As I continue to add randomness, the correlation coefficient crashes, as does my ability to distinguish one, to predict the value of one variable from another. And in fact, when I get a correlation coefficient that's near 0, it means I have no ability at all to predict. You tell me X, and I have no idea where Y is. In this case, see if we can get a real small one. That's like 0.15. So this is the idea of a correlation coefficient. It's close to 1 when the relationship looks very linear, and it's close to 0 when there's no visible relationship between the variables. In other words, no ability to predict one value from the other using a linear equation. Just a note on the correlation coefficient, R is a number that's between 0 and 1, 0 no prediction and 1 perfect prediction, but it can also be negative, and the negative numbers have the same meaning in absolute value. -1 means the same thing as 1 perfect prediction. The negative sign on the correlation coefficient just tells me whether one value increases or decreases as the other changes. So here's the formula for computing the correlation coefficient. It's not really that bad. It looks a little ugly, but what do? I take the X values and I subtract their mean. I take the y values and subtract their mean, and then term by term multiply them together and add them all up. In the denominator of this fraction, I add up the squares of the differences of x from its mean. That would be the first step in computing the standard deviation for x, right? I add those all up. I add up the same for the y variable, the y value minus the mean squared, add those all up and multiply those two together and then take the square root. So it's an ugly formula, but let's look at it for a simple case where my x list has values 2, 4, 6, 8, and my y list has values 3, 5, 7, 11, and 14. So if we list them here, I can first find the mean value of x by adding them up to 30 and dividing by 5. So my mean value of x is 6. I can do the same thing for my y values. The total is 40. 40 divided by 5, because there's 5 values, is 8. So the mean value of y is 8. So if I take my x values and subtract the mean of 6, 2 minus 6 is negative 4. 4 minus 6 is negative 2. 6 minus 6 is 0. 8 minus 6 is 2, and 10 minus 6 is 4. So these are the x values with the mean subtracted. Remember, we did this a long time ago. If I add these up, I get 0, and that's one of the ways the mean always behaves. It's like the balance point in that there's as much negative stuff as there is positive stuff. Similarly with the y variable, the y mean is 8, so I take 3 minus 8, I get negative 5. 5 minus 8 is negative 3, and you're probably already thinking, I could put these numbers in list 1 and list 2, and then generate these in list 3 and list 4, and that's how we'll actually proceed. So now in my formula, I need the product of these differences from the mean. Minus 4 times minus 5 is 20. Minus 2 times minus 3 is 6. 0 times anything is 0. 2 times 3 is 6, and 6 fours are 24. So these are the elements, the product of the differences or residuals that I add up to get the numerator value. So add these up, I get 56. That's what goes in the numerator according to this formula. And now I have one more task to do. I take each of these differences and square them. So negative 4 squared is 16, negative 2 squared is 4, etc. The total of the squares of the differences is 40 for x. And similarly, minus 5 squared is 25, negative 3 squared is 9. I add up those, I get 40. So now I have all my pieces. I got the sum of the squares of the differences for x, the sum of the squares of the differences for y. I multiply those two numbers together, 40 times 80. I take the square root, and that's what I put in the denominator, so 56 divided by that, and I get a correlation coefficient of 0.9899, or a very high correlation between these two lists, because as one list goes up, the other goes up, and they stay kind of in march, and that's basically the idea of correlation. Okay, so time for practice. Pause the video now and work this out. It's not that hard. First thing we need to do is compute the totals and means, right? The mean of the x's is the total in list 1 divided by 6, because there's 6 values. The y mean is the total of list 2 divided by its values, or essentially if you just put this in list 1 and this in list 2, you can compute the means directly. And then for my formula, I'm going to use three lists. I'm going to take each of the x's minus its mean and squared. For list 4, each of the y's minus its mean. So whatever the number is in here, remember I can do something like list 1 minus the numeric value of the mean squared in parentheses for list 3, and I can do list in parentheses list 2 minus that numeric value of the mean from here squared. And then list 5 is simply list 1 minus its mean times list 2 minus its mean. And then I'll need the three totals. The answer for the correlation coefficient is the total of list 5 divided by the square root of the product of the totals down here, as we did on this slide. So see what you can do with that. And we'll show the solutions on paper shortly. Okay, but before we reveal those solutions, finish covering our material. Correlation does not imply cause. This is probably the most important thing to know about correlation. All it does is say that when one value goes up, the other goes up, and when the first value goes down, the other goes down. So here's an example of what's called spurious correlation. There's actually a whole website dedicated to this. The number of people who drown by falling into a pool in a year correlates with the number of films Nicolas Cage appeared in the year, with a reasonably high correlation coefficient of 0.66. In 1999, we start out, and then you see that there was a drop. They both dropped together in 2003, stayed low. There was a peak up in 2007 for both number of people who drowned by falling into a pool and the films Nicolas Cage appeared in, and then they dropped together. It doesn't mean there's any cause going on here. Obviously, Nicolas Cage appearing in films didn't cause people to fall into pools and drown, and vice versa. So this can happen in various ways. It could be just random, or there could be something moving these two values together that has nothing to do with the relationship between them. Okay, here's the idea of how cause and correlation are connected. Here we have some actual causal things. A traffic accident will cause a traffic jam. Heavy rain can cause a traffic jam. Either of these can cause someone to be late for school, either getting up late or being caught in a traffic jam. And a traffic jam can also cause long queues. So we have direct causes. A causes B or B causes A, like the ones where there's an arrow. Heavy rain causes traffic jam, or getting up late causes late for school. There's cases where there's a common cause. That is, late for school and long queues are going to be correlated not because one causes the other, but there's a common cause. Traffic jam will cause both of these. And things can also be correlated because of a common effect. In this case, getting up late is going to be correlated with traffic jams because if you're late for school and one of these is true, the other one probably is not. So these are the ways that things can be related. Direct cause, common cause between two things, late for school and long queues are both caused by traffic jams, or common effect, traffic accident and heavy rain both affect traffic jam. And any one of these kind of causal connections will induce visible correlation between the variables. So again, it's this one that we're looking for, and correlation only gives us a clue that there's something going on, but doesn't tell us which direction, if any, the cause exists. So it's a much more difficult subject. Whole courses are dedicated to deducing cause from data. But one thing we can be certain, if there's no correlation at all between variables, then they can't be connected in a causal way. Okay. When we have correlation that's visible, when there's significant linear correlation, then it's reasonable to actually compute or figure out a line that fits the data. We're going to use 0.7 as the absolute value level as our indicator in the class. When the correlation coefficient in absolute value is more than 0.7, then it's reasonable to model the data with a linear equation. We can do this one way by just literally on a piece of paper drawing a line that kind of splits the middle of the data, but we'll see there's a way to compute it directly. So what we do when we do this is we substitute this line as what we call a model for the data, and then we can use that linear equation, y equals ax plus b or mx plus b, to predict the values of y for the given values of x. And this is a big reason for doing linear regression, is we end up with a model that gives us predicting ability. We can plug an x into the equation. Like if I plug in x equals 3, then the answer that comes out is 3 times 0.7, or about 2.1 plus 0.8, and that would put us on the line right here. Okay, it turns out that you can actually compute both correlation and linear regression directly on the TI-84 without doing all the work that we outlined previously. The idea is simply you put the list of the x values into list 1, and the corresponding, remember, each of these x's and y's are for one individual, so we have to pair them up. So you put the x values in L1, the corresponding y values in list 2, and then we use stat, calc, linreg, and there's good reason why we have to use version that's numbered 8 in the calculator. And it gives us the intercept of the line and also the slope of the line. And there's one more trick with the TI-84. You only have to do this once between resets or changing the batteries, but you need to do this. You hit the second button and then catalog and then diagnostic on and enter twice. Otherwise, you won't get the correlation coefficient that goes with the line. Okay, where do we go from here? Well, you've got a worksheet to work on, and we'll show the answers to the built-in problem here, and also you get to practice with the TI calculator for computing correlation linear regression. And then next week, we'll examine something that's called the coefficient of variation, which is just the square of the correlation coefficient, but it has important meaning. We'll also study how to use and also not use the regression line. When is it useful? What can we use it for? What should we avoid? We'll practice using correlation linear regression on biological data. And one more thing is we'll look at what's called the analysis of variance, or ANOVA, to finish up this topic later next week. But on Monday, we'll do a quiz on both the chi-square test and 2 sample t-tests, preceded by a review. Okay, so that concludes the video. So now you'll be able to work on the worksheet that accompanies this video.